Hello, everyone. Gonna give it like 3, 4 minutes more in case anyone else wants to join in, and then we'll get started. Today is gonna be math. All right, I'll get us started and share the PowerPoint. Today, like I said, it's gonna be math. There aren't too many slides on this since math isn't really like an explicit section on the MCAT. I think on the DAT there are math questions, but it is a skill you're going to need mainly in like the first section, the chem phys section. But in general, a lot of the questions and passages are also kind of study based. It might be like an experiment they ran or something of the sort. So it's still good to like have that kind of stats knowledge and be able to do good like mental math since you aren't allowed a calculator. So one of the things that I think is important to know is scientific notation, which you've probably already had to go through in your classes, but as a reminder, you can kind of write anything as like the number times 10 to a power. And so if you have a negative exponent to get the actual number, you can move the decimal to the left. So like 1.0 times 10 to the negative 2, you would move it 2 spaces to the left to get 0.01. Whereas for a positive exponent, if that was like 10 to the positive 2, you'd move it 2 places to the right to get 100. And so, I mean, it goes without saying, I guess, like if it's negative, the number is going to get smaller. If it's positive, it's going to get bigger. This also translates to the metric system and the prefixes that are used. So like if your basic unit is 1, like 1 meter, that times 10 to the negative 2, that's a centimeter. And if it's like times 10 to the 3, that's a pretty common one, is kilo for 1,000. So also good to be familiar with those in terms of like the units you're going to come across. And in physics and stuff, sometimes you might get a question where something's in like kilometers, but something else is just like in seconds. So if your answer choices are in like meters per second, you want to know how to convert that back. So that's going to be like however many kilometers times 1,000 to get to meters, for example. Another thing to just note is significant figures. I don't think they explicitly ask about this, but it's still good to have an idea of them. So the rules for significant figures, it's basically like when you have a lot of digits, some of them are significant and some aren't. So non-zero numbers are significant. So anything 1 to 9 is a significant digit. Zeros that come between two non-zeros, so if you have like the second last one there, 1002, those zeros are significant because they are still like giving you information about that number. That's kind of what like significant figures means, like which of these digits is actually giving us information. Leading zeros are not significant in the sense that they're just like placeholders. So for the second one, 0.008, those zeros before are not significant because they're just getting the 8 to where it needs to be, if that makes sense. So if you were to put that in like scientific notation, you would just do 8 times 10 to the negative 3. You wouldn't do like 0.0008 times 10 to the negative 3, which is another way to kind of realize like you never put zeros before something in scientific notation. So like those leading zeros are never going to be significant. Trailing zeros, so like zeros after a non-zero, are significant if they're to the right of the decimal. So for the fourth one here, 340, that's the like before the decimal, that last zero. So that's not significant because it's kind of like a placeholder. It's just getting the 3 and the 4 to the hundreds position. Like if you got rid of that 0, it would be a different number. And that's why you need that. Same with like the one below that, like 60, 700. You need those zeros to get them to the thousands and hundreds spot. But the zeros themselves, it's not like you tested it and you found out that number was 0. It's sort of the vibe. So like for like 340, for example, that 0 is not significant. And all that's really saying is like, you know about the 3 and the 4, but like that 0 spot isn't significant. But if it's to the right of the decimal, it is significant. So like the bottom one there, 4.9210, that last 0 is significant because you didn't have to put that there, if that makes sense. Like if you didn't know that last amount of precision, if like the amount you measured was just like 4.921, you would just write 4.921. If someone gave you that extra 0, that means like they measured that extra amount and know that that spot is 0. So it does matter when it's to the right of the decimal. You could think of like you didn't have to put that there, but you did, so it is significant. But when it's to the left of the decimal, like 340, 6700, you had to put that there to get those numbers where they have to be. Another thing that you might see is like a whole number with a dot. So it would be like 340 decimal. And then that 0 is significant, like the decimal usually indicates the 0 is significant there. Another thing is, let's see, we did rule 5. Trailing zeros with no decimal are not significant. So that's just like the other side of what I just said. So again, 340, 6700, those zeros are not significant. 7 is a little different, but basically it's that exact numbers have an infinite number of significant figures, and that's like if they're using a definition, like 1 second, 1 meter, those are like defined units where you're saying like that's like infinitely precise. Like every digit is significant because you know that's exactly 1 meter is what you're using, or exactly 1 second. So that's not the case if you measure something and you say it's 1 meter, but if you're given like something is 1 meter long or something, not as a measurement, but actually like as the unit. And then if we're looking back at scientific notation, if you have like a number times 10 to the something, the number itself, you're going to use significant figure rules, but then like the 10 to the power, like those don't count as significant digits. Like 10 to the 2, those aren't significant. But if you have like 3.4, that's 2, but if it's like 3.40, that would be 3, things like that. Also, a rule for like scientific notation in general is you want to have only one number to the left of the decimal when you're doing scientific notation. That's kind of like the point of it, because you could do like 34 times 10 to the 3, but it's easier to just put like 3.4 times 10 to the 4. So like you always want to just have one digit to the left of the decimal keep it in like the ones, and then you can adjust the exponent to account for like however high or low that number is. So that's significant figures. When you're calculating with significant figures, I got this off of online, but if you want to like hold the right amount of significant figures accurately, if you're adding and subtracting, it's about like the decimal place. And if you're multiplying and dividing, it's about like the actual number of significant figures. So for adding and subtracting, well, in both cases, you want your answer to not be more significant than what you were given, if that makes sense. So for example 1 for addition and subtraction, the least precise thing you got was the 5.4. That only went up to the 10th, whereas the 4.03 went up to the 100th. But that means for your answer, you want to round it to the 10th, because like it's like saying it's like 5.4 something, because you don't actually have that digit, and 4.03. Since that something is fluctuating, you don't want to give 9.43, because the answer, if these were like measurements, it might not actually be 9.43, it could be 9.45, 9.46, because that 5.4 something was never specified. What's after that 4? And so you only want to round to the like least precise thing you have, which is the tenths. And so same goes for subtraction as well. This is where you also want to note the trailing zeros rules. Let me try annotating here. So like this 0 is not significant. So that means like the one that they highlighted, that is the least precise thing, or the most precise that you have. So you go up to the 10s here, whereas this goes up to the 1s. But that means for your answer, you only can go up to the 10. So you round that down to 90. For here, this is what I meant by if you have just like the decimal given, that means all those zeros are significant. That decimal is a way of showing like it's not just like I got the 4 and the 3 and the zeros are there for a place. That decimal is like the person's making the choice to put the decimal to say that those zeros are significant. Like they measured and those 2 are 0 as well, if that makes sense. So from here you have the 1s, from here you have the tenths, which means your answer, you want to round to the 1s. So yeah, addition and subtraction, you're gonna look at decimal place. On the other hand, for multiplication and division, you're gonna just look at the actual amount of significant digits and make sure your answer has the same as the lowest one. So for number 1 here, there's 3 significant digits in this one, but this one only has 1. So for your final answer, you only want to have 1 significant digit. Significant digit and significant figures, I use interchangeably, I already have them, but they're the same thing. So for question, let me fix the screen here. Okay, for question 2 then, the first number 15.64 is 4 significant figures, but then the 30 is only 2. The 0 is significant because of this decimal place. And so you can do the math as normal and then round in comparison to like trying to figure out the digits before. I would say like just do the math as good as you can before and then worry about the digits later if it matters in the question. And then for other questions, for addition and subtraction here, when you have scientific notation, you can still hold that like these are this is like the highest precision you have. So you have to account for the exponents in the sense that one could have more digits. Like if this was times 10 to the 3 and the other was times 10 to the 5, it would be different. So hence they wrote it out. That's the easiest way to figure out like what is the least precise that you have. So for scientific notation, probably easier to write it out there, or else when you have it in the exponent, you're not exactly sure what the places look like. So that's calculating. Also, at any point, any questions or anything, put them in the chat or unmute. I have to clear these annotations. Okay. And then another thing that you're going to be using, which you already kind of have in scientific notation we covered, is exponents. But when you're doing math with exponents, exponents come up quite a bit in your formulas. So like Kaplan, I screenshotted, actually shows some of the common equations that would use exponents or logarithms, sound level, decay, things like that. pH scale is a really important one. So for exponents and logarithms, understanding the math is important. Also understanding how they work is important in terms of like the pH scale and the sound scale, like that you understand like going up 1 is actually like multiplying by 10. Like your pH change of 1 is like a 10 times increase or decrease in the concentration of like hydronium ions or whatever ion, hydroxide, whatever it is. So it's important to be able to like visualize that as well. And then in terms of the math side of things, some good things to note about if you're dealing with exponents is these like equations on the left side there. So zero exponent identities, anything to the zero is just one. Anything to the one is itself is another one. So like x to the one would just be itself. If you're multiplying like bases, so it's like the same number on the bottom, these x's are the same and they have different exponents. If you're multiplying them, you can just add the exponents. If you're dividing, you can subtract the exponents. If you're doing like an exponent and then another exponent, you can multiply those things. So like 4 squared and then cubed. You can just multiply the 2 and 3 and say that's going to be the same thing as 4 to the 6. And then negative exponents are like reciprocals. The negative just indicates that it's going to be the reciprocal of that. So like anything to the -2 is like 1 over that number squared. So it just means you're going to have to put it on the denominator at the end. And then fractional exponents are roots. If it's just like, if your a is 1, so like x to the half, if the top number is 1, then that's just like that root. So that's the square root of x. But in the case they showed here, if like you actually have something in the numerator that's not 1, so if it's like 2/3, then it's like cube root of x squared. So the numerator will still stay as an exponent, but you can think of like the denominator in a fractional exponent as a root. So that's that for exponents. And then on the flip side, logarithms. Oh, gotta clear the annotation. Logarithms are like the reverse operation of exponents. So a lot of these rules you'll notice are the reverse of the exponent rule. So for exponents, like if you're multiplying like bases, you end up adding the exponents. Logarithm, it's the opposite, where if you're multiplying, you can add the individual logarithms, and that's because one thing undoes the other. So like E, by the way, is Euler's number, and so that's just like about 2.718. That is like the inverse of ln, which we call like the natural logarithm. The other version is like the base 10 logarithms, where it's like anything to the 10. To undo that is like log 10. So the complementary, like the operation would be log base 10. You technically have any base, but the common ones are 10 and e. So this ln is the same thing as log e. Yeah, so that's logarithm. So the rules you'll notice are just kind of the inverse of the exponent one. So if you're dividing things, so this is like this, by the way, there's like brackets here. So if your things are getting multiplied within the logarithm, that's the same thing as like adding them outside. Things are getting divided within the logarithm, same thing as subtracting them outside. This is like, these are the equivalent of like anything to the 0 equals 1. So that first rule from exponents, this is like the reverse of it. I guess this is like the same as your x. So no matter what your base is, log of 1 will always be 0. And just to like break it down, this is basically the way the log works is like, what exponent do I have to raise the little thing to get 1? And so the answer is what your exponent would be. That makes sense. So this corresponds to this, that corresponds there, and your base corresponds to like the number being raised. So another example, instead of like x's and zeros, is you could have like log base 2 of 8, for example, is equal to 3. So it's like, what exponent do I have to put on 2 to get to the number 8? And that would be, the exponent would be 3. So yeah, those are the log rules. And then another thing is, for if there's an exponent within your log, this is a pretty cool one. You can just bring that down as a coefficient. This is kind of like reversing the Power of a power is multiplication sort of thing. So if you have like log of a to the b, you can bring the b down outside and just say that many times. And then lastly, same way that the exponents kind of worked, if you have like a reciprocal, you can just bring out the negative and flip it. So that's logarithms. Sometimes for like equations, and since you don't have a calculator, you're gonna have to approximate square roots. Probably not too often, but if you do, one thing is just like figure out which squares it's between. So it's handy to know like the first few squares, which are shown here. And then, for example, if you had the root of 180, so one option is to think like, what two perfect squares is it between? In that case, it's between right now 169 and 196, which are 13 squared and 14 squared. So then you know that the square root of 180 is going to be something between 13 and 14. Since it is logarithm, like an exponential scale, one thing is like your brain might go to like, oh, it's like if something's like just halfway between 169 and 196, it's going to be 13.5, but that is not true, since for squaring you're like multiplying things. So you intuitively might not be able to get a good guess of like where between 13 and 14 it is, but at least that can help you narrow it down to like what it's between. Another way is to also break it down into things you do know the square roots of. So 180, the 18 might remind you of like, that's 9 times 2. So you know, like it's got to be divisible by 9. You can take that out. So this is actually like 9 times 20. So it'd be like the square root of 9 times the square root of 20. And then 20 you can break down into like 4 and 5, for example. And so then if you take out like those perfect square numbers, you can get it down to something like this, which may be easier to comprehend. And like the square root of 5 is going to be somewhere between 2 and 3. So it's like between 6 times 2 and 6 times 3. So it's like, that tells you that it's like between 12 and 18 if you don't have square root of 5 memorized. So I would prefer this method, but you know, whatever works. Memorizing, like being familiar with some of the square roots, like I think square root of 2 and 3 are on the next slide, is also good. Also the number actually ends up being, I think it's like 13.2 or something. And so that's why, like I said, like approximating where it is between these isn't going to help you, because it's closer to 13. But when you look at 180, it's more closer to 196. So in between, you might not be able to approximate, but it is correct that it's between 13 and 14. So you can at least get there. And then based on your answer choices, since it's like multiple choice, that should be enough. That should suffice. So here are the approximations I was talking about. So knowing square root of 2 and 3 can come in handy. You'll also need those for trig, which is in a few slides. So good to know. The next ones I found in the Kaplan book. I didn't know these until I found them in the book, but if it's useful, you can convert between the two types of logs. And for a scientific notation logarithm approximation, so if you're taking the log of something in scientific notation, this is an approximation for it, which I didn't know before, but you can kind of like drop the exponent like you would, but add it instead. And so it's like 0. And so if you have like 4 times 10 to the 2, it's like 2 plus 0.4. So it'd be about 2.4. Haven't tried it myself, but if that comes in handy. Now moving on to trig for right angle triangles. You might need this for example, like in physics, sometimes like your force is at an angle and you only want the cosine of it. Like the cosine between two things could come in handy, or the sine based on like dot product, cross product, which we talked about 2 weeks ago for physics. So like things like work and torque. And so if you have this angle here and this right angle triangle, then the different trig ratios, sine is opposite over hypotenuse. So SOHCAHTOA you've probably heard of is like the mnemonic for it. And so then you have cosine and tangent as well. So like in this case, for example, your opposite is A and your hypotenuse is C. There's also, of course, Pythagorean theorem if you're looking at the lengths of these. So you know this is also true, and then you can use these. It's also, I guess, one way to also remember these is like you memorize them as just like the formula, like, oh, sine theta is like A over C. But one thing to note is like that means that's like the sine theta is like the ratio between these two things, which means if you have one, you can get the other as long as you know the sign. So like if C is like your total force and you have like some force in the y direction and some force in the x direction, knowing this angle can help you find the components, right? So like this was the force, then there's like some upwards amount and some leftwards amount. So if you know like the angle and you know the sign of it, then you can use just like the total force to get to the components. Because another way to write this, right, is that C sine theta equals A. So it's important to note that with the hypotenuse and then the appropriate trig ratio, so sine or cosine, you can get to the other two sides. And then if you have like one side and need the other, like if you have x and need y or something, you can use tangent for that. So it's important to note. Obviously, you're not expected to know like the sine and cosine of like every angle. So there are some special triangles though that you might need to know. Okay, so one thing that I didn't put in the slides, but I could is also like in the table and worthy of noting is like these triangles will cover 30, 60, and 45. Another thing to remember is you can always draw out the graphs for these. So if you have like sine, you should know it starts at like 0 and then it goes up and down. So this is like 0, this is 180, this is 360, this is like 270 and 90. So for those angles, if you end up having to do like a sine or cosine, you can kind of just like picture the graph that like sine of 0 is 0, sine of 90 is 1 up here, 180 and 360 are also 0, and then like sine of 270 is -1. Cosine starts at 1 and looks more like this. So that's for those numbers. And then for 30, 60, and 45, the special triangles come in handy. So I would say it's worth memorizing these ratios. So the 30, 60, 90 triangle is by taking like an equilateral triangle where all angles are 60 and then dividing it into 2, as you see like the line between the dotted line there. And so for that, it's just important to note that like the measurements there become 1, 2, and √3. And it's also like the largest measurement is across from the largest angle. So the largest angle in this triangle is 90. So if you're trying to match like where are each of these numbers, the largest number is 2, it's across from the 90. Smallest number is 1, it's across from 30, the smallest. And even though the 3 may look large, √3, as we saw before, is like 1.7 something. So that's like in between, 60s in between. So that's how you would match those. So you can use this triangle to find sine and cosine if you need, say, sine of 60. It's like the opposite over the hypotenuse, so √3 over 2 for 60. Another thing you could note is that for 60 and 30, sine and cosine, like these are just the numbers. One's going to be half, the other one's going to be √3 over 2. And like one mnemonic that sticks in my head is like 6 is greater, sine is greater, I guess because of the s's. So for 60, the sine is the one that's greater, cosine is the smaller half. So then inversely for 30, the cosine is actually the larger one and half is the sine. That might help. Drawing the triangle will also always work. And then the other triangle is an isosceles triangle because these two are the same length, the 1, 1. If you have 1, 1, then the hypotenuse is going to be √2. You can also use Pythagorean theorem, 1 squared plus 1 squared is equal to √2 squared. And for that, you don't have to really be able to draw the triangle per se, because the ratios work. There should be a 2. I don't know why that says 3. But the ratios will work, like the sine and cosine are the same because your opposite and adjacent side are both 1, since it's an isosceles triangle. So those are some trig ratios to know. Tangent you can also find from, so for the 45, tangent's going to be 1 because the ratio of them is 1 to 1. And then for the 30/60, you can solve out the ratio. It's either going to be √3. There's some errors in this. The tan for 30 should be 1 over √3. Okay, maybe don't trust this table, but you can trust the triangles. So it's going to be from the 30, the opposite over the adjacent. Another thing to know about like sine, cosine, and tangent, which you've already seen here, is like for 2 angles that add up to 90, so for example 30/60, like the sine and cosine of them, sine of one is going to equal the cosine of the other, as you can see here. And then the tans are just flipped because it's like opposite over adjacent. What is opposite and what is adjacent just flips. So like for 30, the 1 is opposite, but for 60, the 1 is adjacent. And then same for the √3. So the reciprocal can get you the tan of the other one. So that's worth knowing. And then, like I said, for 0, 90, 180, 270, 360, you can get those off of knowing the basic graph that we drew in the corner there. So those are the trig ratios that I would consider worth knowing. Another thing, and I think this is more DAT, but you might have to solve algebraic systems. So 2 ways to solve that, if it's like 2 linear equations, would be substitution or elimination. So the way substitution works, as shown here, is take one of the equations. So for example, if your 2 equations are the ones here, isolate one of the variables in one of the equations and then plug it in for the variable on the other one. So they took the 5x equation and you isolated for y, so moved like the other terms to one side, divided by the 2, so you got an expression for y. So you want to take this entire expression and that's going to equal y, so you can plug it in for y in the other one. And then you'll be left with only x's, and you can solve for x. As shown here, you go down, you find x, and then you can use either of the equations in its original form to find y out again. So this is like my preferred method, but another one that works for people as well is elimination. So elimination is like you add or subtract the equations together to get rid of a variable. So in our equations, none of the coefficients are the same. So like we have, there's a 3, 4, 5, and 2. So you can't like straight up add them or subtract them, but you can multiply. So the 4 and the 2, for example, if you took this whole equation and multiplied it by 2, then you would get like a minus 4y, and this is also a 4y, and that could help you eliminate it. So as they do here exactly, you'll be able to, whoops. So you'll be able to multiply that whole equation, and then you either add or subtract them together based on the signs. So in this case, you have plus 4y, and then in the other one it's minus 4y. So you want to add those together to get like 0y and eliminate y from your equation. But if they were both plus 4y, you'd want to subtract. And then you're left with an expression for only x, and then just like before, solve for x, plug that into either of the original equations to get back y. So that's solving systems. Another thing is math in research. So this is this part that I would say is more applicable to like even like the psychology or biology sections, where a lot of times they give you a scenario of a study. And so there are some like statistical concepts that you might want to know about. So I think I mentioned this during the sociology review as well, but one thing is like reliability and validity. So this like diagram of the dartboard kind of helps show it, but your reliability is how close together your darts are, in the sense that if I were to do this study again, would I still get the same thing that you did? So these two are unreliable because the darts are pretty scattered, but these two on the bottom are reliable since the dots are all kind of close together. So it's like reliability relates to like precision, like your study was pretty precise, like you kept ending up in the same area. And then accuracy or validity is like, was that area the correct one? Sometimes in research, you don't actually know what you're answering in like novel research, but sometimes you, like in this dartboard case, you want to be near the center. So the top two are invalid because whether they're close together or not, they're nowhere near the center, whereas the two on the right are at least zoned in on the center. This one is unreliable because it's all over the place, but you can tell like it's still in the general right area. The one that's unreliable and invalid is like, not only are you scattered, but you're also missing the mark. And this one, you're scattered, but like towards the center. And then this one is obviously the best case scenario. It's precise, they're all together, and it's valid because they're all in the center of the bullseye area. So that's the difference between accuracy and precision. Another way to think of precision is when we did like our significant figures or significant digits. It's like, how many of those significant digits do you have? So like if the true answer is like 2.5, if you get like 2.5132, that would be like both reliable and valid. Like not only are you right, and you also got it like very precise, accurate and valid. Something that's like precise but not accurate is if you got like 4.13956. Like if you got like a ton of digits, that means it was like very precise. You somehow measured down to like, if this was like meters, for example, you could like measure down to nanometers. But if it's not even near the right measurement, if it's not even near 2.5, then it's not accurate. And then getting 3, for example, if you only measure to the nearest meter, then that is accurate or valid, but it's not precise. You didn't get many like digits in that measurement. So that's kind of the number equivalent of this drawing. And so, as you probably know, for research, there's like independent and dependent variables. Independent are the ones you change, and then you see what happens to the dependent. And there are controls that you use. Basically, everything other than those variables should be controlled. There's also negative and positive controls. So positive control is that like the dependent variable changes when it should, and then negative is that it doesn't change when it shouldn't. So if you're running, say like you're running a gel in bio or something, and you're trying to see the bands, a positive control is something where you already know where the bands should be. Like you already know that I have exactly like a 30 kilodalton or something, and then you make sure that it ends up there. So that means like your whole gel wasn't wonky. And then a negative control is to just put something blank, like run water or something. And if even water shows, or like something blank shows up as like protein or RNA or whatever you're looking at, then you know that something went wrong. Like it was probably contaminated, something got into all of them, because something that you know there should be no result, and something that you know exactly what the result should be. You kind of want both. So like in my lab, at least, they always make us put both so that you are sure on both ends. So known sample, and then like a blank. Blank is like common name for negative control. So that's that. Error in studies, there's many ways to have errors. So some that they say are like bias, confounding, or random. Random kind of goes without defining, just could come up with anything. Bias is more systematic though. And so that's if there's like a problem when you're collecting your data. So the 3 types they kind of describe is selection. So like the sample you selected is different from the population. This is when you're studying humans mainly, where it's you can't study everyone in America, but you want a sample that's like representative of America if you're if the conclusions you're drawing are supposed to be for America. So if you sample Hopkins students in a survey and then you try to put those results to America, that's going to be a selection bias, because just being at Hopkins, insinuates you have certain privileges or access to things, and that's not like representative. Or you're even like a certain age group, that's not representative of the whole country, for example. So then detection bias is when you use your knowledge by searching for an outcome disproportionately. So it's kind of like when you already know what it's supposed to be, or like you already have an answer in mind. So you're kind of biased in the numbers you see or like what you're trying to study. So this is more like the researchers themselves already have anticipating something, and the way their study goes is almost like confirming what they already think instead of actually questioning. And then the Hawthorne effect also comes up in psych soc, but it's like the changes in behavior when you know you're being observed. That could happen actually from the subject or the experimenter, but especially like the subject, if you're like interviewing or asking someone about, say, like their eating habits, they might say that it's way healthier than it is. Or like if you're testing manners, if someone knows that they're being observed, they might, say please and thank you more because they know. But if you just had a camera and secretly recorded them, they might not have said it. So that's like the Hawthorne effect. And then confounding is a common connection between the dependent and independent variable. So this is like the most common confounding variable in like a lot of studies is like socioeconomic status. But like it's when there's like another reason, there's a third variable, and you're saying these two things are connected, but it's really that third one that's playing into effect. So like I heard like this study of like different sports and like which sport makes you healthy or something, and they said like horseback riding is the one, like horseback riders are the healthiest, but then the confounding variable was again socioeconomic status, where on average horseback riders were the most affluent group of athletes, like compared to some other sports might not cost as much to play, like soccer or something. So those were the most likely people to like have really good health insurance, like always access like medical needs and like preventative care and stuff like that. So like it's not the horseback riding that made you healthier, it's the fact that you were rich that allowed you to do both horseback riding and take good care of yourself and like have all those amenities in the medical system. So that's like an example of confounding. So that's like an error in the study where the conclusion wasn't necessarily the real truth about which sport makes you the healthiest. It's not necessarily that sport that caused you to be as healthy as you are. Validity and significance. So validity we already talked about with the dartboard, but there's internal and external validity. So internal is just like is more of the dartboard situation where it's like the relationship, the causality you're seeing in your two variables is correct. Whereas external validity can this be generalized? So like internal is like exactly what you're studying. Did you see the right thing? But then external is like, are you like the broader conclusion you're trying to draw, is that also correct? And like the population you're trying to describe. And then another thing, you have to have significance statistically and clinically for a study to be supported. This is from Kaplan. I'm assuming they mean like medically related studies. Statistical significance is like the p-value and stuff you see in stats, and it basically measures like how likely is it that this was just by chance you saw this. So ways to like increase statistical significance is like if you use a lot of subjects, like rolling all heads could just be from chance if you only roll a coin like or flip a coin twice. But if you do it like 100 times, that's way more significant to get like 100 heads in a row than 2 heads in a row. To see something like by only doing it twice versus doing it like 10, 15 times, more significant. So then that lowers the odds that it was from chance. Like it's not by chance. If it's like a study and you're manipulating something, if you see it this many times, it's probably not by chance. And then clinical significance is just like, should people care? Kind of like, is this important to patient care and outcomes? So it's just like, why are you studying this? So that's what I had for the slides. If there's any questions, I'll take them now. Otherwise, there was one more section in the Kaplan book I wanted to go over. And that was like the more stats part, but feel free to unmute if you have any questions while I reshare. Okay, if not, this is the last chapter of the Kaplan book. They put like physics and math together. It's mainly physics in this book, but like the last two are math. There's just like, I think it's a good summary of like the stats things that are important to know. So when I say like statistically significant, we can elaborate on what that is. Also, they say like the types of charts and stuff are like probably the most high yield part of this chapter. So central tendency is the first part they talk about. So mean is like sum everything up and divide by how many numbers you have. So sum of all your numbers divided by like you have n amount of numbers, that gets you your mean. That's like the most common central tendency that is used. And it's better when things are close together. Outliers can change that data. Like if you have, especially if you have a low n, but if like one number is wildly ridiculously high from everything else, your mean is going to look much higher. You could have like 5 numbers really close together and a sixth one that's super high, and your mean is somehow like between the 5th and 6th. And so this is better for when things are closer together. So average income is a good example of how like the mean gets skewed, because some people have so much money that the average income sounds much higher, but half the population makes less than 50,000, even though the average is 70,000. So it's like those high income ones are outliers. In those cases, people use median, and median is just like the middle of the data. So if you have an odd amount of data points, like you have 5 things, it's your third. If you have an even amount, you take like the 2 in the middle. So if you have 6 things, it's like the average of the mean of your third and fourth. So you can find like the position of the median by just like the total plus 1 divided by 2. If you get a decimal number like 9.5, that means it's between the 9th and 10th. So that helps. This is good when there's outliers, and that's why for grading and stuff too, a lot of times professors will publish both, but a lot of times they use median if there's like a lot of outliers. The mean might not be representative. Like if everyone did generally well, or like everyone got above a 60, but one person just didn't do the exam and they got a 0, it's going to bring down the mean a lot. You'd rather have the median to be more indicative of like the class overall did well, other than like the one person who didn't take it. So that's the median. It's also nice because then exactly half is above and half is below. Mode is not really used very often, but it's just the most common one. And then for distribution, so there's a lot of talk about like normal distribution. That's like the bell curve here, and it kind of splits off into how many standard deviations away you are, and about 68% is within 1 standard deviation. So that's like the dark blue. So from your mean, you're 1 standard deviation above or below, and then 95% within 2 and 99 within 3. So that's why it's very central to the mean. So supposedly MCAT scores are also on a bell curve. And then on the other hand, if not everything is towards the center, it could be a skewed distribution, as so could be skewed negative or positive. And these you'll just mainly just recognize when they give you a graph. Bimodal is when there's like 2 different peaks. And so to measure distribution, one way is range, which is just like highest minus lowest, like this is what the data ranged from. There's also the quartiles that people use. So interquartile range is between the third and the first quartile. So it's like a quarter, like 25% of the way through and 75% of the way through. I think they also mentioned quartiles. Yeah, so quartiles just divide the group into 4. So the way kind of like the median divides it into half, if you found like the median of the first half and then the median of the second half as well. So you have 4 even chunks. And your interquartile range is those 2, like the median of the first half and the median of the second half subtracted. Standard deviation is a very common one, which we also talked about in the bell curve. And so this is the formula for it. So what you do is you take every point and you see how far is it from the mean, and then you square that. Part of the advantage of squaring it is that it doesn't matter if it's above or below the mean. because negatives and positives, once you square them, become the same number. So you sum up like every data point, how far is it from the mean, and you square it, like sum up all the squares. So square first, then sum, just to be clear. And then you divide it by either n minus 1 or n. So they use n minus 1 when you're generalizing to a population. And then, so that's what they say to do for the MCAT. So that would be your standard deviation. And so that's like for a bell curve situation, like we said, like about 68% would be within one standard deviation. So for example, they gave you like these data points. First thing is to find the mean. So you can actually see like the difference between each point. So find the mean, and you see how far is each point from the mean, and then square that, sum up all those squares, and divide by how many numbers you had minus 1. So this is an example where square root you might need a square root approximation. So going back to what we said, right, this is between 16 and 25. So you know your number is going to be between 4 and 5. It's 4.18. So, official like definition of an outlier is anything that's more than 3 standard deviations from the mean. Since like we saw in the bell curve, like about 99% of things should be within 3 standard deviations. So, yeah, so there's 3 ways to find an outlier. So a true statistical anomaly, like a person over 7 feet tall, so it's like just truly an outlier. Measurement error, so like something went wrong that time. And then a distribution that's not approximated by the normal distribution. So if you have a data set that, like, for example, is skewed or something like that, you might get a lot of things that end up being outliers because it probably just doesn't fit the idea of a normal distribution around the median. Okay. For probability, we talked about like independent and dependent variables. So if you've taken prob stats, I guess you've seen these, but there's like the intersection and union. So probability of 2 or more things happening is the product of them happening alone. So if you want to see like A and B both happen, the intersection, if you know the individual probabilities, you can multiply those. So for example, like heads twice in a row, you know getting heads once is 0.5, so you'd multiply like 0.5 times 0.5. Or if you want to like flip a head and then roll a 2 on a dice, then it'll be like 1/6 times half the 2 individual probabilities multiplied together. And that's like what we call the purple section there in the Venn diagram. The union, so one or at least one of the 2. So just a head or just a 2 or both a head and a 2. What you do is add probability of A and probability of B and then subtract the probability of both. And that's because you're going to count that purple area twice. If you take the whole pink circle and you add the whole blue circle, that overlap part, that purple is there twice. So you have to kind of subtract out the purple. And then for hypothesis testing, so there's the null hypothesis, which is usually the one where it's like this is just like by chance, or like 2 things are equal or something. And the alternative one is where like you're saying something happened to make it the other way. So populations are not equal, or it's like directional. And so you probably won't have to calculate these yourself, but it's important to know that like if you have like a p-value, then that's basically like the likelihood it was by chance, and so you want that to be less than a certain amount. The researchers will decide what that significance is. So like most commonly you'll see 0.05. So p less than 0.05 means your results are significant. So then you can reject the null hypothesis that like null, like nothing's going on. But if it's greater than that, you fail to reject it. So p greater than alpha, fail to reject it. So it's not a statistically significant thing. There are different error types. So truth, the truth could be that there's no difference or there's a difference, and then your conclusion can be to reject or fail to reject. So you could be correct, or you could have type 1 or 2 errors. So if there is no difference, but you say there is, it's type 1. If there is a difference, but you fail to see it, then that's type 2. And then confidence intervals is like, if you want to be a certain amount confident, then like something has to be between here and here. So it's kind of like you reverse it. So you begin with the desired confidence level, and then you find the score for it. But you probably won't have to come across this during the test. How are we doing in time? Oh, okay. This is I think there's only 2 more subsections left. Again, feel free to put questions in the chat if anything comes up. So this is what they call the high yield part of this chapter, and that's the charts. You're probably familiar with pie charts. Everything adds up to 100%, and you have the different chunks of them. So this is like population. Then there's bar charts and histograms. I would say, like, I'm sure from doing practice tests and practice questions, you're getting better with reading information. There are like a lot of charts and like a lot of data being presented to you across all of the sections, so it's important to know. Box plot is one you might get, and it's maybe rarer to see. So box plot plots the median and then the first quartile and third quartile levels, as well as the entire range. So the box itself is like the Q1, Q2, Q3. So like median, and then like the median of the top half. So that's like Q3, Q1 here, like the median of the bottom half, and then the range. So like the highest and the lowest numbers. So these tails are called like the whiskers. I think it's called like a box and whisker plot as well. Yep. So you can get a lot of data out of there. Maps, obviously, and then you could have like a color scale tell you data about it. Yeah, relationships, you can have linear, parabolic, exponential, or logarithmic. So the exponential and logarithmic are just like inverses of each other, as you can see. They're like flipped across the y equals x line because one undoes the other. Also important to note, like, this is what we mean by like pH scale or something, for example, where like pH of like a step up in pH rate is 10 times. So like you can see how fast this graph moves. So it's important if something's measured in like an exponential way to realize that like +1 doesn't sound like a lot, but it's like 10 times. Slope equation. Yeah, I think that, okay, so semi-log, another thing is like when you're graphing log data, sometimes they want it to look linear to show the log ratio, and so the axes can be put into logs. And so as you can see here, like the ticks are not uniform, but that's like to make something logarithmic look linear. So you might come across something like this. It's important to take your time when counting these ticks as well, because something will look halfway in between, but it's not. As you can see, if this is like 10, yes, this is 10, 20, 30, 40, 50, and then like 60, 70, 80, 90 are very close together. Like 80, 90 barely look different, and you're at 100. And then this is the difference between 100 and 1,000. The first chunk here is just the difference between 0 and 10, then you go from like 10 to 100. So pay attention to those and read those well with the tick marks. We're pretty much at time. I'll stay back if there are any questions. Otherwise, this is pretty much the math review I wanted to give. Tomorrow is going to be Orgo review, and then there's also Wednesday and Saturday like group study. If you have any questions about any of this to say for then, feel free to come by. But otherwise, yeah, thank you guys for coming. Thanks for coming.